When dealing with voltage drop calculations for roadway lighting using a common neutral, several factors come into play. Firstly, the use of a common neutral introduces complexities due to current flow and vector analysis. Unlike a simple single-phase circuit, the current in the neutral conductor is not necessarily the arithmetic sum of the phase currents. Instead, it is the vector sum, which can be lower than the arithmetic sum if the phase currents are balanced. Secondly, the long circuit lengths, ranging from 1500 to 1800 feet, exacerbate the voltage drop issue. Longer conductors have higher resistance, leading to greater voltage drop for a given current. The goal is to maintain the voltage drop within the allowable limit of 5%. If the conventional voltage drop formula is applied without considering the common neutral, it may overestimate the actual voltage drop, leading to unnecessarily large conductor sizes. Therefore, it is essential to account for the effects of the common neutral when calculating voltage drop. There are generally two approaches to address this problem, either using a computer program designed for this type of calculation or employing a longhand formula that accounts for the vector nature of the currents. When selecting a computer program, it is important to ensure that it is capable of handling multi-phase circuits with common neutrals and that it can perform vector analysis to accurately calculate the neutral current. Some electrical design software packages include features for voltage drop calculations in complex circuits, considering factors such as conductor impedance, load characteristics, and circuit configuration. Alternatively, a longhand formula can be used, but this approach requires a more in-depth understanding of circuit analysis and vector algebra. The formula would need to account for the phase angles between the currents in each phase and the impedance of the conductors. The vector sum of the phase currents would then be used to determine the neutral current, which would then be used to calculate the voltage drop in the neutral conductor. The total voltage drop in each phase would be the sum of the voltage drop in the phase conductor and the voltage drop in the neutral conductor. To ensure accurate voltage drop calculations, consider the following steps. 1. Determine the load current for each lighting pole. This will depend on the wattage of the lamp and the supply voltage of 277 volts. Use the formula amps equals watts divided by volts to calculate the current. 2. Determine the phase angle between the currents in each phase. Since the poles are connected to different phases, the phase angles will be 120 degrees apart. 3. Calculate the vector sum of the phase currents. This can be done using Phasor algebra or by resolving the currents into the rectangular components and then adding the components. 4. Determine the impedance of the phase and neutral conductors. This will depend on the conductor material, size, and length. Consult conductor tables to find the impedance per unit length and then multiply by the circuit length. 5. Calculate the voltage drop in the phase and neutral conductors. Use Ohm's law, which states that voltage equals current times impedance, to calculate the voltage drop in each conductor. 6. Calculate the total voltage drop for each phase. This is the sum of the voltage drop in the phase conductor and the voltage drop in the neutral conductor. 7. Compare the calculated voltage drop to the allowable limit of 5%. If the voltage drop exceeds the limit, increase the conductor size and repeat the calculations. In addition to the above steps, consider the following factors that can affect voltage drop. Firstly, temperature. The resistance of conductors increases with temperature. Therefore, it is important to consider the operating temperature of the conductors when calculating voltage drop. Secondly, conductor spacing. The spacing between conductors can affect the inductance of the circuit, which can also affect voltage drop. Thirdly, the presence of other loads on the circuit. Other loads can draw current and contribute to voltage drop. Fourthly, harmonics. Harmonics can increase the RMS current in the circuit, which can also increase voltage drop. To mitigate voltage drop issues, consider the following strategies. Firstly, use larger conductors. Larger conductors have lower resistance and can carry more current without excessive voltage drop. Secondly, reduce the circuit length. Shorter circuits have lower resistance and lower voltage drop. Thirdly, increase the supply voltage. Higher supply voltages result in lower current for the same power, which reduces voltage drop. Fourthly, use voltage regulators. Voltage regulators can maintain a constant voltage at the load, even when the supply voltage fluctuates. Fifthly, balance the load. Balancing the load across the phases can reduce the neutral current and voltage drop. Lastly, use power factor correction. Power factor correction can reduce the current drawn by inductive loads, which can also reduce voltage drop. Remember to consult the National Electrical Code, or NEC, for specific requirements related to voltage drop and conductor sizing. The NEC provides guidelines for calculating voltage drop and specifies the minimum conductor sizes for various applications. NEC Section 210.19 A1. FPN number 4 recommends a maximum voltage drop of 3% for the feeder plus branch circuit. NEC Section 215.2 A1. FPN number 2 recommends a maximum voltage drop of 5% for feeder conductors. And NEC Section 310.15 provides tables for determining the allowable ampacity of conductors. When performing voltage drop calculations, it is important to use accurate data and to consider all relevant factors. Overestimating the voltage drop can lead to unnecessarily large conductor sizes, which can increase costs. Underestimating the voltage drop can lead to equipment malfunction and safety hazards. Therefore, it is essential to perform thorough and accurate voltage drop calculations to ensure the safe and reliable operation of electrical systems. When working with electrical systems, it is important to follow all applicable safety precautions. Always to energize circuits before working on them, and use appropriate personal protective equipment, such as gloves and safety glasses. If you are not qualified to work on electrical systems, consult a licensed electrician. Remember that electricity can be dangerous, and it is important to take all necessary precautions to prevent accidents. When designing roadway lighting systems, consider the aesthetic and environmental impacts of the lighting. Use energy-efficient lamps and fixtures, and minimize light pollution by directing the light downward and shielding the lamps. Also, consider the impact of the lighting on wildlife and the surrounding environment. Designing a safe, reliable, and efficient roadway lighting system requires careful planning and attention to detail. By considering all relevant factors and following best practices, it is possible to create a lighting system that meets the needs of the community while minimizing its environmental impact. When you are designing your system and choosing your materials, remember to consider future expansion of the roadway lighting if possible. This could save time and money for additional improvements down the road. It's also beneficial to keep accurate and up-to-date documentation of all electrical work for the roadway lighting system, including circuit diagrams, voltage drop calculations, and equipment specifications. This documentation can be helpful for future maintenance, troubleshooting, and upgrades. This information may also be required to show compliance with local regulations. In addition, it's useful to keep track of any changes or modifications made to the system over time, noting the date, reason for the change, and the person who made the change. All of this will ensure efficient operations going forward.